Hi, I'm Chahat.
And I'm Apurva.
For the CSE564 Final Project, we are doing 5,000 years of solar eclipses visualization. And the sun, the moon, and the earth are constantly involved in a celestial dance. These movements throughout years show various trends, both in the geospatial as well as the temporal domains. Through this project, we aim to answer questions such as, do eclipses occur after any periodic intervals, or are certain types of places on Earth more susceptible than others to witnessing solar eclipses?
First, let's look at the geospatial analysis. On the top left here, we have a choropleth map. This map shows the frequency of eclipse in each country. The higher the number of eclipses that the country has witnessed, the warmer the color is. For example, here, if I hover on Russia, I can see that it has the highest number of eclipses, that is 1048. Now, if I click on Russia, I can filter the eclipse patterns in all the other graphs for Russia. When I look at the donut plot here, I can see that the highest number of eclipses are partial eclipses, that is shown by red. Similarly, if I select Canada, I can see similar trends. The 69.1% of eclipses are partial. Similarly, Greenland, which is also in the northern hemisphere, has 73.9% of partial eclipse. Now let's look at the southern pole. For example, Antarctica. It also has 67.5% partial eclipses. But if we look at if we look at a country that is closer to the equator, such as Brazil, we can see that there are no partial eclipses in Brazil. And if we select India, we can see again that there are no partial eclipses. This is showing a very obvious trend that partial eclipses are more popular in the northern and the southern extremities of the latitudes. This happens because of the sun's obliquity and the sun being lower in the horizon in the northern and the southern poles. The moon has a higher chance of passing the sun and causing a partial eclipse. Let me reset here. And we can also see this trend displayed in the scatter plot in eclipse latitude versus eclipse longitude. The red dots are the partial eclipse, and you can see that at the latitude extremities, the partial eclipses are more common, and in between, other eclipses are distributed.
Since we're talking about the scatter plot, we have allowed the user the functionality to pick what variables they want visualized on the scatter plot. But to help guide the user through this, we have provided the MDS attribute similarity plot, which shows the correlations between the various attributes. So let's take the example of gamma and eclipse latitude, which are correlated according to the MDS attribute similarity. Updating this to the gamma variable here, we can see that gamma is at the extremities of the earth, that is at the very high or the very low latitudes. We can see that we are seeing more of these red partial eclipses, whereas near the middle, the other types are kind of scattered throughout. And talking about gamma itself, it's basically a magnitude that shows how centrally the moon's shadow passes across the earth. So near the equator, the gamma will be 0, whereas as we move further from the equator towards the poles, more specifically towards the North Pole, gamma will have more and more positive values, whereas moving downwards from the equator towards the South Pole, we'll see lower values of gamma in the negative side. And this, again, filtering to show, say, only the partial eclipses, will again confirm the thing that we already knew, that partial eclipses occur more towards the extremities of the earth. Let's try looking at another thing on the scatter plot. Let's change this to show the variation between gamma and eclipse magnitude, for example. I'll add the rest of the eclipse types back. Now this shows a very interesting trend again. At the top here with the highest magnitudes, we have the total eclipses. Total eclipses occur when the moon fully covers the sun, and that's why the eclipse magnitude is so high. Lower over here, we have the annular eclipses. Annular eclipses are the ones where the moon covers the sun but leaves a ring of fire around it. So obviously the magnitude should be lower than the total ones where the moon covers the sun fully. Lying in between them, sandwiched here, are the hybrid eclipses, which are a combination of both of these. And obviously the lower eclipse magnitudes are all covered by the partial eclipses.
Next, let's look at the temporal analysis. Here in the time series plot, we can see that average eclipse magnitude is plotted against the decades. So we can see how the magnitude of the eclipse has varied over the years. We can see that there is a very obviously discernible pattern here, that eclipses are cyclic events and their patterns repeat after a certain period of time. Here I've also included a functionality to select a time frame. For example, if I want to see the eclipses from 1500 BC to 500 BC, I can select I can brush over the plot, and all the other plots are updated based on that. Here I can also move the brush across and visualize different decades and their eclipse patterns in different decades. Now let's look at the constellation frequency map. This is a radial stacked bar chart which shows the frequency of eclipses based on the different constellations visible during a certain time period. So this shows more of the yearly trends of eclipses as compared to the decade trend that is shown by the time series plot. Here we can see that the most frequent type of eclipse happens when the Virgo constellation is visible, and fewer eclipses happen when Scorpius or Cancer is visible. So what we understood from this is that it might be because when Virgo is visible, it is during the August and September months, which is when the autumnal equinox takes place, which means because of the longer days, the more number of eclipses can be seen. And similarly, Cancer is associated with the month March, during which vernal equinox takes place, and because of the sun's movements and sun and the earth's movements during these months, there are fewer number of eclipses. I can also filter based on the types of eclipses, and I can include or exclude any number of constellations and visualize the eclipse trends for that. This graph also shows how many nighttime and daytime eclipses are occurring. So the purple shows the nighttime and the green shows the daytime eclipses. So now if I brush over the past years, for example, sometime during BC, I can see that nighttime eclipses were more popular, and now in the present time and in the futuristic decades, I can see that daytime eclipses are more common. This is also due to the Earth and the Sun's movement and the Earth and the Sun's movement and its patterns. Another salient feature that we have included is in the choropleth map. If we zoom in, we can see these white dots, which are eclipses that are witnessed from major cities. For example, here I can see an eclipse in New York that happened in 1984, and it was a daytime eclipse, and it was witnessed for 11 seconds.
To add on to the temporal analysis, we can observe various different trends throughout the decades here on the scatter plot as well. For example, the decade versus the inter-eclipse duration shows us that these eclipses tend to have a periodic pattern where they occur after certain specified durations, such as most partial eclipses occur after 30-year intervals, whereas the other types generally occur after either 150 or 180 years. Let's look at when most hybrid eclipses tend to occur. And we can see that most hybrid eclipses tend to occur after, say, 180 years generally. So this is again a periodic pattern that we uncovered.
This shows that hybrid eclipses are not as frequent.
So in conclusion, we did a geospatial analysis, and our analysis mapped the trajectories of solar eclipses across the globe, and it revealed that certain latitudes and longitudes are more susceptible to experiencing solar eclipses, and also the type of solar eclipses. We also did a temporal analysis which showed how the periodic patterns are in eclipse magnitude as well as other variables as well.
Thank you.
Thank you.